So we have third presentation by Jeroen Audenaert. Jeroen is a research scientist at MIT, leading the development of machine learning and artificial intelligence techniques for NASA's transiting exoplanet survey satellites. He obtained his PhD from KU Leuven. Prior to joining MIT, he co-founded a company called Yellowleaf, which was acquired in 2023. It's my pleasure to welcome Jeroen, and his talk is entitled Physics and Device-Aware Foundation Models. Let's welcome Jeroen.
Hi everyone, very excited to be here today. So today I will talk about specifically physics and device-aware foundation models. Now, in space science, we're making lots and lots of types of observations, and all of these are made with different types of instruments. We have different types of satellites, each with different biases. If you're making specific measurements, depending on what type of instrument you will have a different bias. And what I mean with this, you might, for example, have very noisy measurements, but longer time series, or you might have very high resolution measurements, but then at a much more cadence, like at a much shorter time scale, essentially. And the same holds for if you're actually making sensor measurements on Earth. Every type of measurement you make, there's a certain bias. And if you want to combine the data from multiple different satellites, this is actually becoming a big problem. Because then you have a bias in each of your data points that you're observing. And if you want to combine all of this data into one large machine learning model, it's actually important to take this into account. And that's where today I will talk a little bit about is how we can actually take instrumentation of our satellites into account where we're building foundation models. Now, just a high-level overview again of what well, I can use the arrows. Perfect. Yeah, so probably most of you have actually seen this nice image of a foundation model. And I don't think I need to go into the details exactly of what you can do with a foundation model right here. But essentially, we are learning some kind of representation that we can then use for all of different types of downstream tasks. And the reason why we can actually take advantage of this right now is because we have lots and lots of unlabeled data. And when we are able to train our machine learning, perfect. Should be okay, yeah. So when you are able to train our machine learning models on more data, we'll actually get better predictions, of course. Now, in order to learn such an optimal representation, we just feed our algorithms lots and lots of data sets. So here what you see here on the left, as one of my expertise specifically lies in time series analysis. So what we're doing is we're gathering lots and lots of time series, and then we try to learn some kind of optimal machine learning representation that we can then feed as the basis for our downstream tasks. Now, in the last couple of presentations, you've already seen what contrastive learning kind of high level is, but essentially, in the case of supervised learning, we have lots and lots of different labels, right? Now, in the case of self-supervised learning, we don't necessarily have all these labels. So what we want to do is, if we want to train our machine learning algorithm, rather than us being able to tell this image is a cat, and it's similar to that other image of a cat as well, we don't really have that. Same in the case if we have two different types of images. If you have a cat and a dog, we don't really know that's quite naturally because we don't have labels in this case. So therefore, one of the techniques that you can use for this is contrastive learning, for example, where you actually do this based on augmentations. So what you can do here, you just take your original image. This is based on a Sinclair paper. And what you say is, OK, we're going to augment this image. And what our model is, we're going to tell it, OK, the augmentation of a grayscale version and a blue scale version image is actually the same type of image. So our model should be able to actually learn these type of underlying characteristics and put these closely together in the latent space. And a lot of the different types of foundation models that we see nowadays are based on this type of underlying methodology. So if we take a case at geospatial foundation models, which you've seen a couple of different slides in the past two presentations as well already, we're just combining lots of different data types. So, and we're kind of training these to actually recognize similarities, for example, in the data, such that we can afterwards use these for downstream applications. Now, on the one hand, in the case of geospatial data, you have space and airborne sensors. So you have a lot of different types of satellites. You have optical, hyperspectral, but you also have UAV sensors, where you have thermal information or just simple RGB colors. Now, all of these are, as said, can be satellites in space or also airborne sensors. Now, on the other hand, we also take a lot of different types of data on Earth, right? You have Earth-based sensors that are, for example, monitoring the water level. But you also have sensors that are actually monitoring the atmosphere. And all these different types of sensors, when we combine them, or we have sensor fusion, this is actually what gives us the predictive power of our models. Because when you combine different data streams that are all observing the same type of phenomenon, this is truly where the power of machine learning can come in, and where we can make much better predictions than if you would just be using one type of sensor data. Now, this is a specific case for geospatial foundation models, but we're seeing actually a very similar type of data structure for other types of foundation models as well. And one of the things we are building at MIT, specifically for the NASA test mission, are astrophysical foundation models. So now we don't really want to build foundation models actually to study life on Earth, but we want to find life outside of Earth ultimately. And the first step in actually building these type of models is actually building a foundation model that can combine all the different types of sensor data streams from space-based telescopes such as the TESS mission, Kepler, or even James Webb, together with Earth-based telescopes. Now, there are a lot of similarities between what I showed in my previous slide, geospatial foundation models or astrophysical foundation models. All of these satellites essentially use sensor data as their underlying data stream. So, for example, in this case, we have lots of time series. As you can see here on the bottom, these are a couple of time series we're actually observing here. We also have spectra, same as you have for Earth observation satellites, or we're actually taking images of the full sky as well. So there's a lot of interdisciplinary science that we can actually do with these types of foundation models. And the techniques we develop for one field are easily transferable to other types of fields. And I think that is a key thing in AI nowadays, that we shouldn't just limit ourselves to one type of data type, because one of the big benefits of training your AI model on astrophysical data is, for example, that a lot of the data is just open source. You can just gather the millions of time series we have over there and use that as the basis for your model. And then afterwards, you can fine-tune it or retrain it to do more Earth-specific applications, for example. Now, just a little bit of an overview of the TESS mission, so you have an understanding of what exactly we're trying to build. So TESS, or the Transiting Exoplanet Survey Satellite, was launched in 2018, and essentially observes the sky in patches of 27 days at a time. And we make a measurement every 200 seconds of around 4 or 5% of the sky. So it's a lot of data that we get in, and each of those images that we get contains about 2 to 10 million stars. So it's a lot of data that we are essentially gathering. And here you can see what actually one sector of data looks like. So this is 4 cameras, and each camera consists of 4 CCDs, or charge-coupled devices, that actually record the observations. And then after 27 days, we switch to the next field of view. Now here you can see what such an image actually looks like. So you have those 4 cameras. You can see on the left actually what the TESS satellite looks like. And then you see there's millions and millions of stars over there. So an image like this contains a lot of information. And how we can extract that, there's a lot of different types of methodologies. You can either just look at all these images and then, for example, look for asteroids that are passing by the field of view. That's more easy if you look at the image domain. But it's a lot of data, because if you want to analyze each of these millions of stars directly in the image domain, it's a lot, because we have 200 seconds that every 200 seconds we're taking such an image, and it's about 10 million of them per month, and we have 10, so it's about 10,000 measurements multiplied by 200 multiplied by 10,000. So lots and lots of data, that's the key thing. Now, one of the ways you can actually do signal processing, and a first step to getting more easy to train data with your machine learning models, is to actually do a first type of extraction. So if you have your satellite data, we have all these different images. What you can do is you can identify each individual star in there, and then you can, for example, make an aperture mask around this. So this is what I'm showing here. You're just identifying the pixels of interest. Very similar to what you would be doing in an Earth observation case. You identify what could be interesting. So we have about 10 million of these per month, and then we measure that brightness. Now you can see here, this is what you get over time. This is called, in astrophysics, it's called a light curve, but essentially you're just measuring the brightness of a star over time. And what you see here, it's a double system where you have two stars, and once one star passes in front of the other, you would actually observe a dip in the observed brightness. Now, if you want to look for planets, this is very similar. So you have your star. If the planet passes in front, it's actually just a dip in the observed brightness, and that is the way we can actually look for planets outside of the solar system. So now that you kind of know what the data, or where the data is coming from looks like, this is actually how our different types of time series look like. So you have exoplanets, for example, in here. You also have asteroids. So if you look at the image level, I don't know whether it's showing up, but yeah. So you see an asteroid passing by the camera, for example. Now, if you would actually make such a light curve there, you would just see that we observe an increase in brightness, for example. So a couple of other examples. Here you can just see what these different types of time series look like. And the reason why I'm showing all these different types of data is just because whether you're observing sinusoidal time series here, or you're making these measurements on Earth, where you have sinusoidal variations in atmospheric pressure, for example, or in CO2, the underlying data processing methodologies are highly similar. And this is something that where we can really take advantage of, and we should really take advantage of, because if we can develop techniques that are able to work on astrophysical data or on biomedical data, both of these can actually benefit all of the different types of fields. And that is one of the key things we're trying to work on in our research group at MIT, just seeing which type of interdisciplinary methods we can develop for this, and actually help us both improve our AI methodologies and also really drive the kind of astrophysical and exoplanet science we can do with this, for example. Now, one of the things we recently did in this sense was actually using the Moment time series foundation model. So Moment is a transformer-based time series foundation model, and it was trained on all types of non-astrophysical data. So it was, for example, trained on ECG signals, human activity, together with some space data from atmospheric sensing, I think it was. But it didn't include any type of astrophysical data. And this is quite interesting, because if you use such a general purpose foundation model, which has never seen any type of astrophysical data, and now we apply it to some type of astrophysics data, specifically from the TESS mission, we actually see that the model is able to distinguish between the different type of physical classes we observe. Now, what I'm showing here is a UMAP plot. So specifically, we took the latent space of our model, so the underlying representation, and then just ran about, I think it's about 20,000 astrophysical time series through this. And the exact classes don't really matter, but what I want to show here is we use this general purpose foundation model, applied it to TESS time series, and it's actually able, if you color code it according to the underlying classes, you see that it nicely separates out the different physics of that. So this means that there's a lot of power in just using general purpose foundation models and then applying them to dedicated physical problems. This can either be in astrophysics or can be of any type of physics. And this is also what we actually found a couple of years ago earlier when we use biomedical processing techniques from, for example, ECG signal processing, as you can see on the left, and you then apply it to the light curve of a pulsating star. So a pulsating star is very similar to what you have on Earth. You have star quakes, similar to how you have earthquakes. So they behave very similarly. And when you use these ECG signal processing techniques and you apply them to astrophysical data, they perform very, very well. So specifically, we use a technique that was actually used originally to distinguish between healthy and sick patients based on their heart rate. And now we found that it actually enables us to distinguish between different types of stellar pulsations or different types of star quakes. And this really shows that signal processing techniques are very universal, and that we can actually really by transferring techniques developed for one domain and we apply them to another domain, we can make the biggest possible progress. And I think it's very important that we keep on training our machine learning models with very, very diverse data sets, because this is actually how we can improve our machine learning performance. It doesn't really matter whether you train your algorithm on atmospherical time series or you do it on astrophysical time series. As long as your model sees a diversity of time series with different types of complexity, this is actually where most of its power will gain from. And then afterwards, of course, you can fine-tune it, But in the first steps for general training, any type of time series data is very valuable, I would say. Now, moving a little bit to also more dedicated foundation models, especially for physics. Of course, you can train on every type of data, but sometimes to start, it's easy to just take the small data set and then you start adding more and more data. So in the case of astronomy, what you do, you take some spectra. So this is similar to how you would obtain hyperspectral imaging in the case of Earth observation data, but for our case, we just have one-dimensional spectra. You combine it with images, and then you can create some kind of shared embedding space. And that's the high-level idea of how you create these foundation models, of course. But one of the things that we actually notice if you try to combine the data of multiple satellites, or even within the same satellite, but under multiple observing conditions, you actually see some issues popping up. So here you see from the Euclid mission, as I'm showing you on the left over there, and you see what the internal latent space of the model looks like. Now, the model did amazing work, but one of the problems we see that on the right side, you actually see all this data, these images of galaxies you could see, for example, on the right, you just see noise in that. So you have this nicely constructed latent space, but then we also have a big part where just all the instrumental systematics are actually kind of put in by the model. So kind of this data becomes very useless because you cannot do any science with it, right? If you see this is full of instrumental characteristics, then how can we actually use this data? Now, especially when you go to a more broader domain, if you try to combine it with sensor data from other satellites, so let's say, okay, we have our observations from Euclid, but we try to combine this with other satellite observations, and then we use one type of bad data, but we try to combine this or fuse this with sensor information from another instrument, then we'd actually have combining bad data with good data, and this might make our shared latent space not very scientifically accurate, I would say. So you would actually be losing a lot of the information. So it's very important that your model can actually deal with these different types of instrumental systematics. And this was just within one survey, right? So if we even re-observe that same galaxy, now maybe a few years later with the same mission, we might already see two different types of data, right? You have one image because maybe the observing conditions were bad here, but in the next iteration, the observing conditions are good again, and you're still trying to fuse two types of data, or well, the same type of data, but with two different types of characteristics, essentially. So it's very important that we take this into account. And in order to do that, maybe just to show you a little bit more of what actually this looks like. So, for example, one of the effects you can actually see here is scattered light. So what you have is if you're making observations, for example, scattered light from the Earth and the Moon can actually reflect off your lenses over here, so of the lens hood. So you see this black thing. Scattered light kind of reflects of it and then hits the camera detectors. And this is in the case of astrophysics, but you have very similar things for Earth observation, as I will show you in the next slide. And what scattered light does is it completely makes your observations useless. So if you look at these images, so these are the 4 different cameras, and then you can actually see the black is the scattered light hitting your detectors. So if your target of interest falls in one of these regions, this means probably that a couple of days of observations, we cannot really do anything with this, because all these effects are actually influencing it, and the stray light is hitting our detectors. Now, in the case of Earth observations, you also have very similar things, right? You have stray light from the ocean, for example, that can reflect, or you have other type of stray light that can also hit your camera detectors. And this is really problematic for a lot of the type of science you want to do, because we cannot use any of that data. So having the right correction techniques is a very important thing here, I would say. For example, recently an ERC was actually awarded to someone in Belgium to actually start on improving a lot of stray light corrections. So this is a big problem, because the better we can actually remove scattered light or any type of systematics, the better our accuracy overall will be. And a lot of you know that in machine learning, garbage in means garbage out. So if we feed kind of these types of images full of scattered light into your model, well, the model cannot really make any good predictions, right? So it's very important to actually keep instrument effects, such as observing conditions or systematic strengths from your satellite into account, I would say. Essentially, if you take a look at what this looks like on a high level, you would see that any signal is combined of your target signal, which is, for example, a sine wave, as you can see on top, together with some type of systematics. And this can be very simple. It can be a linear trend. So if you just add a 2, you see some kind of slowly rising sine wave. But ultimately, if you want to study our target, we first need to remove the systematics. And the same in the image domain. You, for example, have this observation on the right that you see, and then you apply some kind of filter over it because of different observing conditions. So everything that we observe is always a combination of how we are observing something and what we're actually observing. Now, even like if your observing conditions would be perfectly okay, the thing is that your detector response can also change over time, especially in the case of space missions. As your satellite is longer and longer in space, you can actually have detector aging, for example, as well. So nothing is stationary in that sense, and that's why we need to combine this into account. We need to combine these two and actually take into account the different type of responses that we can get there. Now, the nice thing actually is that often we know the structure of the data. We don't have any specific labels on what exactly we're observing a priori, but we know when we are observing certain targets and what the location of all those targets is, right? So if you take a more detailed look, for example, here at some time series examples, so on the left you see the time series of brightness measurements for a particular target star. So you see this was observed in sector or time window 14. It looks quite nice, but if you look at the plot on the right, this is just immediately 1 month later, you already see that the systematic trends look very different, right? So this is the exact same target, but just 1 month later, and this is because some observing conditions were different. So this shows that we need to take it into account. Underneath, you see data from the previous NASA mission, the Kepler mission, and here it actually looks super clean as well, and that's because the pixels were much smaller in this case. So if we would be combining these 3 types of data, we actually really need to take into account these characteristics. But because we have overlapping observations, we can actually do this. So specifically in the case of TESS, we're actually re-observing stars the whole time. So here I'm just showing you a sky coverage plot. But you can see that actually over time of the mission, at the moment we're up to sector 95 or something, and we have covered about 98% of the sky. And we have up to 4D times of repeated observations. So we can actually use these repeated observations and actually take an advantage of this to build survey agnostics embedding. And the key to doing this is because we're observing the target under varying instrumental conditions. And that's how we're actually able to build such survey agnostics embeddings. Now, what I mean with this, you have your typical foundation model that I showed you the slide before. And what we're going to do is, rather than training a single latent space, we're actually going to train 2 separate latent spaces. So what you're going to have is you're going to have a physics latent space that capture the underlying properties of the system that you're observing, and then we're going to have an instrument latent space. And this instrument latent space is actually going to capture all these different types of systematic effects that we are potentially observing. And specifically, this is called a causal foundation model. And the way this works is by taking advantage of overlapping observations. So here you can see the arrow over here. So we take a random, for example, a random star that was observed during time window 41, let's say. So you see, okay, this is what it looks like. And then in order in the physics space to actually construct this one, we just take an observation of that same star, but observed under different instrument conditions. So we just take, for example, that same target, but observed in sector 50 or during that time window. And you can already see, although the signal looks similar, the instrumental differences are quite significant, right? Here you have this rising trend, while here are just very stable, because there was less scattered light, for example, in that sector. Now, this is how we construct our physics space, by just giving a lot of examples of that same target observed under different instrument conditions. And then if you look at the instrument space, we do the same thing. We just take any random target that was observed during that same time window, and ideally on the same camera, and specifically on the same region, on the same pixel region as well. And when we take a random star in that same sector, you can actually see that it shows quite similar overall systematic trends, right? And by giving the model a lot of different examples of this, we are actually able to then construct an instrument space and a physics latent space. Now, once you have these 2 types of latent spaces, we're actually able to offer much better predictions for the cases of classification, anomaly detection, or parameter inference, for example. Now, we initially validated this on a lot of different types of simulations. We just took time series here, but you can do it for any type of data, right? So what we do is, for example, if you look at the middle one, the black lines are actually what we're observing, but the red lines, well, they're a little bit faint, but the red lines are actually the true signal. And that's, for example, because of a detector that can only observe a maximum brightness, you would actually have a certain type of cutoff. Or you would, in the case of here, you would have some kind of scaling factor that actually, that makes it much more difficult to observe the real signal, and we have some kind of distortion, right? Now, if we actually train such a model on this, these are the results that you can see here. So if you visualize your two different latent spaces and you take the two-dimensional equivalent of those very high-dimensional latent spaces, you get physics latent space and an instrument latent space. Now, if you look on the left side of this latent, on the left side, which is the physics latent space, and you color code it according to the instrument number or the sector in the case of test, you would actually see that there's no correlation at all. But if you color code the same thing according to the period, so just if you have a sine wave, you take the period of that, and we can actually see there's a beautiful correlation according to that, and same to the amplitude. And it's important to note that we never gave our models any information with regards to period or amplitude. It learned these all from itself, right? And then if you do the same thing for the instrument latent space, you see that it's nicely color-coded according to the instrument number, but it does not specifically actually capture any information with regards to the period as well. So this is very promising because it shows that we're actually able to disentangle these two in some sense. Now, what I showed here is for a relatively simple set of simulations, but we made this in a much more complex case as well, and we see that it still works, but there might be a little bit of overlap as well. So if you take a look at these two latent spaces again, you see the physics latent space is still uncorrelated according to the instrument. The instrument still shows a little bit of correlation, and here you have some slight overlap between the two. But effectively, it's still able to disentangle all of these measurements, which is actually very good. And if we look at some comparison metrics to a typical foundation model, which only has one latent space, so just we train your traditional foundation model, you have one latent space, we can actually see that we are performing much better. If you try to predict a certain type of stellar parameter, you can see R square is predicted here, and then you have the number of training samples, and the red curve is the causal foundation model, so the one where we have two different latent spaces. We can actually see that we are outperforming single latent space foundation models by quite a bit, and especially if you compare it to some kind of MLP, we're also much, much more better. So what this implies is if we don't have a lot of labeled data, and we separate out our two latent spaces, we achieve a higher performance. You actually get about like 65% R square for about 10 samples already, which is a lot. Compared to what you would need to get otherwise with an MLP, for example. Here you would need a lot more. You would need on the order of 10 to the third number of labeled samples compared to only needing 10. So that's a big difference. And if you compare it to a single foundation model, there's still already quite a big difference. Here I'm just visualizing the accuracy over time. So the right one is actually is how quick we get there with a causal foundation model. And on the left, you see an MLP, so a multi-layer perceptron, just a simple neural network, while in the middle one is actually trained on a typical foundation model as well. Now, if we apply this in practice, we're actually finding some very similar results for Kepler and TESS. So these are the two different NASA missions. If you combine the data, we can find already that it's nicely able to separate out the different telescopes, and also according to the time window when exactly it was observed. These results are preliminary still, but it's quite nice that we can actually find these things already. And one of the good things that is actually coming out of such a model is that you can also use it for conditional instrument generation. So what I mean with this, if you take the example on the left, for example, this was done by one of the PhD students at MIT, but if you take, for example, one of the fashion MNIST data sets, so it's just a publicly available data set, you take, for example, a pair of trousers, and what you can do is you can conditionally generate that under a different type of filter. So, okay, you have another filter. We also have something that's observed. It's a blouse, I think, here. It's at a rotation of 75 degrees together with a scale of 0.5. We can say, okay, now I want to generate that trousers, but under the same filter. So this means that we can just reconstruct that pair of trousers under the same filter. And this is actually quite nice because it allows us to build much, much better instrument models. And if we have much better instrument models, we are able to correct our data to a much more higher accuracies, and we can improve the type of science we can actually do with this. And it's the same thing if you're doing it for astrophysics or any type of geosensing type of data. You have your target, you have an instrument, and then essentially with your instrument model, you can take a look at what exactly this would look like. And we took the case of fashion MNIST because it's much easier to visualize this thing than compared to some type of astrophysical time series you're observing, actually. Now, one of the problems we're still seeing with more general astrophysical or more general time series foundation models is that, ironically, they're not able to deal very well with time. So, for example, what I mean with this, if you have data observed at different sampling rates, so you have a 10-minute sampling rate, 200-second sampling rate, and 30-minute sampling rate, the model actually puts them in different parts of the latent space, which is quite interesting, and it shouldn't be because this is the data for the exact same targets. So you're just observing that same target, but at a different sampling rate. The model just separates them out in different parts. And this is something that really needs more improvement, because for the same target, you want to make sure that your model actually combines all of this data together in the exact same latent space. So what you want is you want to have your model look like this. So this is what happens when you sample it all to the same cadence. You just downsample 200 seconds to 30 minutes. And then you get this nice picture that I showed earlier before as well. But it's something that still requires a lot of work, and that we're actively working on seeing, okay, how can we better incorporate this time aspect? And it's not always important depending on the science goals, but especially in the case of complex data sets, we really need to be able to do this. And one of the larger things we're trying to do now, for example, is actually try to just scale up this whole approach that we're doing. So you're combining test data, as I'm showing here, together with LIGO data as well. And then we also wanted to work for other types of applications. So you wanted to work on biomedical data and on, for example, wearable data as well. And the idea here is the more, as I said before, the more data you kind of put into your model, the more varieties it can learn, and the better it can work on it. And of course, we won't be feeding the exact same things at the same time in that model, but you just can use it for different types of training systems. And then you can use such a downscale methodology depending on what exactly your science goal is. Because by training on large and diverse data sets, you actually we see that you get a lot of improvements. And this is what I showed in one of the first slides. If you take a general purpose model trained on biomedical data, you can already get a great insights into astrophysical data. So therefore, we're just trying to take all these different types of data, train our model on all these different types of data sets, and see what the performance there will be for downstream tasks. And one of the things we did in that sense is actually trying to build, for example, the multimodal universe, where we're actually releasing a big benchmark. It was published at NeurIPS last year, and we just allow the machine learning community to use all types of astrophysical data to train their models on. So whatever data you have, you can actually use this, all types of astrophysical data, and use it to train your models on. So now lastly, before moving towards the end of the end of my presentation, one of the things that we actually see nowadays happening a lot is that we just have such a large data volume that we're not always able to deal with it. And this is okay in the case of large corporations. You have lots and lots of compute. But sometimes you just only have a limited amount of computing resources. And it's important that you actually are still able to run your AI algorithms, right? So one thing you can also do is run all your models on compressed data, especially in the case of UAVs, for example, if you want to do onboard computing, or even if you have limited downlink rates to send your data back to the main processing center. You can actually just run it on compressed data. And this is something that I came across a couple of years ago when I met a colleague who, working at UC Louvain, who was actually working on training deep learning models on compressed data. And this shows actually, it seems to be working very well, because you're saving actually, you're saving data transfer rates, and you still only get a slightly lower performance, and you can kind of choose a certain threshold where you want to apply it on. So if you're able to live with 80% accuracy and 85% accuracy, you might be able to save 5 times on the data transfer rate while still getting a very high accuracy. So this is something that's quite cool if we can actually check how much more we can run on compressed data as well. So yeah. This was the kind of the last slide I had. Just a couple of takeaways from my slides. As I said it multiple times, we need to take the hardware of our satellites into account to actually be able to build better models. We build interdisciplinary models, and this will actually, in the end, result on better foundation models, I would say. Thank you.
Thank you very much for a very exciting talk. we are open to questions, please. Okay.
Thank you for the exciting talk, as Danda said. I'm curious, what projection strategy did you use to visualize the embedding spaces in 2D?
Yeah, so we've used a lot of different ones. You can use a simple PCA one, principal component analysis. You can also use TSNE, or mostly we use UMAP because it uses manifold learning specifically, so it looks for the lower dimensional equivalent based on the topological structure. And we find that UMAP works is the most computationally efficient one, and it can also capture nonlinear relationships. If you take a PCA one, it's more interpretable, but then it cannot really capture any type of those nonlinear relationships, so it's not always optimal in that sense. But ideally, if your data is linear, I would always stick to PCA because it's much easier to interpret.
Yeah, thanks. Also, it seems to me like in the visualization where we see the general model separating the classes, it actually seems to me that they're not that perfectly separate. Like we see definitely a lot of stuff gets isolated out, but there's also a lot of stuff that's sort of overlapping, and it makes some sense. There's probably some time series which are vastly different, so the model captures that, but there's probably something that it doesn't. So did you do like a more qualitative analysis on actually how much sense this makes and whether it actually captures something meaningful, or it's only able to like differentiate between the most obvious stuff?
Yeah, so I think it's mostly able to differentiate between the most obvious stuff. Like if you want to have like high-level separation, the models can still do that, but you will need some fine-tuning. So I would say that general model is great as a baseline model. You can just apply it and you will get a relatively decent accuracy, maybe let's say like 70%. But then, because it has never seen any type of astrophysical data, you will not nearly get to 100% accuracy, right? So then you need to fine-tune it on on the data type you actually want to use it for. And then you will be able to improve your accuracy.
Yeah, that makes sense. Thank you.
More questions? I have one question in the meantime. So when you are doing this alignment of the optical and then the spectral data, it appears to me they are rather quite complementary, and maybe it's not easy to derive information from one to the other. Unlike this image text alignment, let's say text alignment is text encoding is not much a problem, then one can hope that most of the text information can be extracted from the images. Therefore, you can bring them into clip-like contrast settings. Whereas in these settings, what you described today, it looks more of the complementary than one may not be able to really derive spectral information from the optical or vice versa. Then do you think that existing such kind of contrastive learning-based methods are still suitable, or something more needs to be done there?
Yeah, I think they're actually still suitable. The data types are indeed very, very complementary, I would say that, because you can get much more information from the spectral domain than what you could get from the time series domain. The thing is, we only have a limited amount of spectra because it's much more expensive to actually obtain this. So usually for one particular target, you might have like between 5 and 20 spectra, while you have on the order of 10 to 20,000 of time series measurements. But I think by combining them with contrastive learning, you still get a lot of valuable information, because it depends a little bit when your spectra was taking as well. So if you only have one spectra, it can already give you some information, of course, on what type of target you're dealing with, what type of star it is. So it adds a lot of value, and I think we've seen actually that by combining these two, you already see improvements in performance, I would say there. But it also depends, for example, if you have a planet and you're taking your spectra at the moment just when that planet passes in front of your star, you will actually see a different type of structure in your spectra than compared to if you would just be taking a spectra when the planet is not in front of that star. So it's even there when you have your spectra, it's important to take into account when exactly this was observed in time, and you need to kind of feed in this vector to make sure you're not giving it biased predictions.
Okay, all right, thank you.
If you looked at the world that you're working in through the lens of utility for astrophysics, what are the 3 top projects or most urgent kind of challenges you have to address in the next months and years?
Yeah, I think the first one is, so right now, because we have we have 10 million light curves or time series coming in each month, we're actually trying to automate the whole exoplanet detection process. So previously what people did is they just looked at all those time series manually and then found what could potentially be an exoplanet. Now we've built the AI pipeline where we actually automate all of this, and humans only need to look at about 100 time series a month anymore, and the rest is all done by AI. So I think that's amazing. But what it does so far, it can only find known planets or known types of planets. So the classic transit one that you could see there, but you also have more interesting type of planets, such as, for example, a disintegrating planet where it starts evaporating, but that doesn't fit our standard template. So if we modify these foundation models to deal with that, we can actually find more interesting scientific cases as well. Apart from that, what we also want to do is we want to expand this more towards the image level as well. So we can, for example, use it better to find asteroids as well. And this is actually one of the key priorities of NASA, as well as planetary defense. So if we are able to use test information for that, that is another high priority one. And then I think overall, just being able to have better cross matches between all the different types of satellites NASA and ESA have, I think that is a very high priority case as well. Thanks.
All right. Thank you very much. So Jeroen will still be around today and then tomorrow as well. So feel free to reach him out directly and interact. With that, let's thank Jeroen again for his exciting talk.